Within the circulatory system, we have several pressures that we want to consider. And first of all, remember in the systemic and the pulmonary circuit, the systemic circuit goes out to the entire body, and the pulmonary circuit goes from the heart to the lung. So it's so much shorter distance. And because of that, the change in pressure that's required for the pulmonary circuit is quite a lot smaller. In fact, if we look at our range of measurements in the systemic circuit, we have 80 to 120 millimeters of mercury. That's the pressure. And within the pulmonary circuit, it's just 10 to 25 millimeters of mercury. So two things here. First, as I said, the pulmonary circuit is just a shorter circuit. So when we look at our Poiseuille equation, Q equals pi r to the fourth delta P over 8 theta L, if L is small, that means that delta P doesn't need to be very big either in order to keep the same flow rate. You should have the same flow rate in the systemic and pulmonary circuits because, you know, it's a closed system and all that blood is going around. It has to go around it with the same volume flow rate. But the pressures are going to be much different because the length of those circuits is smaller. And then also just want to remind you that this measurement that we have, this millimeters of mercury, is based on this idea that if I have two pressures, one pressure here, we'll call that P1, and here P2, I have a difference in these pressures. This is the big pressure it's pushing down, and it's pushing down so that I have this height or this column of this liquid. And if this is mercury, then my measurement would be in millimeters of mercury. If you've ever been to a hospital, the blood pressure cuffs aren't really the same way now, but they used to have a thing attached to the wall, and there was like a little vial or like a glass cylinder that was filled with mercury. And as the nurse or doctor would take your blood pressure, you could see that move up, and that's how you would measure the um, the blood pressure. Also, the blood pressure measurements, are these gauge? Or are they absolute measurements? Well, of course, these are gauge measurements, and I just want to remind you that the absolute pressure is equal to the gauge pressure plus the atmospheric pressure. Okay? When we're talking about blood pressure, there are two different numbers, and I'll sort of give you the ideal numbers. This is the systolic pressure first is 120, and that's sort of your ideal amount. The pressure when the heart contracts. So it is the higher of the two pressures. The systolic pressure is the when the heart contracts. And in fact, systolic means contraction. I don't know why they don't call it the contracting pressure, but anyway, the lower number is the pressure when the heart relaxes. And this is called the diastolic pressure. Diastolic pressure is the pressure when the heart relaxes. And diastolic means a drawing apart. So it's like when the heart, you know, relaxes, it gets bigger, and then that pressure is going to go down. Also, we can apply Boyle's law in this case. Not really Boyle's law. Remember, Boyle's law says that PV is equal to some constant value. Really, Boyle's law is really only supposed to be for gases, but we can sort of apply it to the heart if you can sort of apply it to the heart. That when the heart contracts, the volume goes down and the pressure increases. The heart applies a pressure at contraction. That's the systolic pressure. And that increases the pressure throughout the entire body. That's why you can feel your heartbeat on your wrist, which is, almost a full meter from your heart, because blood is incompressible. And the Pascal's principle will apply to this system, that when I apply a pressure to an incompressible liquid in a closed container, which is what I have effectively, then it will be felt throughout the entire container. Let's look at one more thing. As blood moves from the aorta to the capillaries, um, we've already talked about how the aorta is about this big. You can sort of fit your pinky inside of your aorta, but the capillaries are really, really small. And so, if we're looking at our continuity equation, the cross-sectional area times the velocity of the blood flow is equal to, or has to remain a constant value. Remember, this is just saying that the flow rate has to remain constant, but the flow rate Q is equal to the area times the speed. Right? In fact, if we look at the units here, this is meters squared, this is meters per second, so this gives me cubic meters per second. So that's good. Now, what happens as the blood, as it moves from the aorta to the capillaries? You might say, well, if I'm moving from the aorta to the capillaries, that's sort of like this situation, where you would say this is the aorta, and these are the capillaries. That wouldn't be correct though. While it is true that an individual capillary is really small, the total network of the capillaries is actually bigger. And so really this situation is the opposite. As I move from the aorta to the capillaries, or a better way to, the aorta is here, and then I move into the capillaries, and of course the capillaries are divided up into thousands of different vessels. So the area of the capillaries actually goes up, and so the speed of the blood flow in the capillaries is quite slow. So the speed of that will decrease. Also, as the blood flows through the aorta to the capillaries, the pressure differential drops. And so what happens then to the flow rate? All right, if the pressure differential drops, then that means that um, to the flow rate, well, this is kind of a trick question because I have this Q is equal to pi r to the fourth times delta P divided by 8 eta L. While it is true that the pressure differential drops, the overall radius of the capillaries goes up. And so this will remain constant. The flow rate always remains the same. All right, and here, let's see, the overall area of the capillaries is bigger. So even though the capillaries are getting smaller, the overall area, the combined area of those capillaries will remain the same.